Good day. Today I will present the work could an electron-positron collider at center of mass energy 240 GeV be used to study top quantum physics? This presentation will be fast given the time. I will omit some elements, but this work will be available soon. The top quark is the heaviest fundamental fermion within the Standard Model, and its large mass is associated with a large Yukawa coupling, which is quite different from the other fermions. This aspect of the flavor problem has been studied for some time, and it is believed that its resolution will require some physics beyond the Standard Model. Many of these models, which follow different approaches, predict new phenomena, such as flavor-changing neutral currents, which could be used to prove the assumptions involved in the construction of such new models. But could BCEPC considered a source of top quarks? In this work, we study the possibility to produce a single top quark in association with a charm quark using FCNC interaction for a particular scenario within a theoretical framework that extends the Standard Model. Namely, we show work within the context of the so-called left-right mirror model, which is left-right model that also includes mirror fermions that are singlet under the SU2 left of the Standard Model, but transform as doublets under a new SU2 right gauge symmetry. In the left-right model with mirror fermions, the right-handed component of mirror fermions transform as doublets under the new SU2 right. The Standard Model fermions are singlets under the SU2 right, whereas the right-handed mirrors are also singlets under SU2 left. The field content is summarized in Table 1. The symmetry breaking is realized by including two Higgs doublets. The Standard Model 1 and its mirror partner. The scalar fields are parameterized as follows. The vacuum expectation values of the Higgs field are. The symmetry breaking pattern should be as follows. The most general potential that develops this pattern of BEV is. After the symmetry breaking, the neutral Higgs boson square mass matrix that follows from this potential is. Diagonalization of the Higgs boson square mass matrix is straightforward using a real basis. So the neutral physical steps are. The mass matrix for the gauge boson is obtained from the kinetic terms for scalar in the Lagrangian. The mass matrix for the neutral gauge boson is now diagonal and is given by equation 7. However, this matrix can be diagonalized by an orthogonal transformation R, which relates the weak and mass energy steps and is given by equation 8. Once the rotation is done, it is found one massless state and two massive states with eigenvalues given by. In order to find the couplings of the Higgs fields with the neutral Gauss boson, we expand the expression for the covariant derivative mu at mu prime, substituting the physical states into equation 5. We obtain the following expression for the CC-Phi interaction. As far as the coupling between neutral scalar and W boson is concerned, it is given by equation 10. The renormalizable and Gauss invariant interaction of the scalar W and Phi' with the electron are described by the Yukawa Lagrangian, which takes the form as follows: the equation 11. The corresponding Yukawa Lagrangian for the quark fields are written as follows: equation 12. For the electron sector, the non-diagonal mass matrix M takes the form as follows: the equation 14. Thus, the mass matrices can be diagonalized through unitary matrices U subscript A for A equal LR as equation 15. We write U subscript A as equation 16. Finally, once we have obtained the quark's electron mass and state, their Gauss interaction can be obtained from the Lagrangian as shown in the equation 18. The neutral current term for the multiple phi of a given electric charge, including the contribution of the neutral Gauss boson mixing, can be written as follows: equation 19. Using equation 15 and 16, one arrives to the following expression in terms of the mass and states. Now see phenomenological analysis. To have a realistic numerical analysis, we need to analyze the three LRMM parameters in space involved in subsequent calculations, namely mixing angle between the neutral Gauss boson C and C', data, matrix elements eta, elf, lambda, right, and C' Gauss boson mass. When Fe, Fj equal Tc and along with lambda r and theta are determinate the flavor changing coupling CQE, QJ and C' QE, QJ. From equation 20, we first analyze mixed angle theta by using the Higgs boson signal strength. The signal strength is defined as follows: equation 23. Figure 1a. The light orange area represents the allowed region by signal strength tau, and the same for all of them. Thus we present in figure 2 this plane which shows the allowed region by the expected upper bound and branching region. We observe in a general way that the behavior of lambda r is increasing as eta L decreasing. Figure 3 shows signal proton-proton to C prime branching relation C prime to LL as a function of C prime Gauss boson mass for eta R equal 0.1 and eta R equal 1. We summarize in table 2 the setting values of the L, R, M parameters used in our calculation. Besides, for further analysis, we define the following scenarios. The process electron-positron 2B, 2TC, 2ELF, nu, BC receives contribution and 3 level from Gauss, C and C prime boson. The Feynman diagram is shown in figure 4. Although we have included both contributions in the simulation, we only present the contribution on the C Gauss boson in the production of the TC quark pair. We present on the left axis of figure 5 a general view of the cross-section as a function of the center of mass energy from sqrt to 500 GeV for scenarios A, B, and C. Meanwhile, on the right axis, we show the number of events produced considering an integrate luminosity of 5000 femtobar minus 1. Figure 6 shows a general overview of the behavior of signal events but for the final state. Let us first define both the signal and background processes. Signal. We concentrate on final state that include the semi-electronic decay of the top quark. Background. The main standard model background processes come from process electron-positron 2 QE, QJ, L, nu, L, where QE, J are like quarks. Figure 7a shows the reconstructed mass of the top quark both for the signal and background processes, and they integrate luminosity to 5000 femtobar minus 1. While in figure 7b we display the same but for the digit invariant mass distribution. Figure A shows the Charm jet energy distribution. As far as the B quark energy from the top quark decay is concerned, its energy is given by equation 25. Then, in order to isolate the signal from the background, we select events with exactly one charged electron and leads to jet which one of them is tagged as a B jet. We consider a B tagging working point with 0.8 efficiency for the B jet and a mistagging rate of 0.1 from C jet. In addition, we apply the following kinematical codes. Figure 9 shows the signal background efficiency plane after applying codes. Figure 10 shows the signal significance for 175 and 210 GeV as a function of the integrate luminosity for scenario A and C. Finally, summary and conclusion. The FCNC processes are a key piece in providing a signal beyond standard model. In this work, an FCNC process between the top and chance quarks we analyze through a B-neutral gauge boson. The C-prime boson is arranged from the considered model, the LRMM, which was our theoretical framework. The singlet top production has been studied and the CEPC, which has been proposed as the next HAP World Project. We conclude that an electron-positron collider and center of mass energy equal 240 GeV could be used to study singlet top quantum physics related with FCNC. Thank you.